those of you who are obviously here because Brian is speaking, and I don't blame you because I'm sure it's going to be really entertaining. So it's my pleasure to introduce Dr. Brian Henderson. Brian is an associate professor of science education here at Arizona State University, and he's a recipient of the ASU Centennial Professorship for Outstanding Teaching, Leadership, and Service. He was named National Academy of Education Spencer Fellow. He is very well published in the highest impact science education journals, and in fact, he plays an editorial role on several of them. And he's also somebody that I actually have really enjoyed discussing science education with since I came to ASU, and in particular, physics education. I don't think I'm lying when I say Brian really has physics in his heart. It's something he enjoys doing as well. So I don't believe in long introductions, so I'm going to hand you over to Brian to hear all that he has to say. Thank you, guys.
Can you all hear me okay? I really appreciate you taking a part of your day to come and listen to me. So back in 2006, I was teaching college physics, and I was trying to implement various things that I was hoping would make the experiences for my students a little bit more interactive, a little bit more engaging, a little bit more motivating than the experiences that I had as a graduate student in physics. But to be honest, it was kind of haphazard how I was implementing things. I would just get suggestions and I'd try them out and think maybe they were working, kind of hope they were working. But the reality was that I didn't really understand much about how the brain worked. And so I decided to go back to school and study how people learn. And so it's been wonderful because over the last 2 summers, I've had the opportunity to teach physics here. And it was my first time in a decade and a half teaching physics, now revisiting physics with some of the ideas that I picked up in my study about how people learn stuff. And so I want to share some of those ideas with you today, but I want to tell you right now, I'm not going to say, okay, I've got the silver bullet, one size fits all strategy for how we should all teach physics. The reality is that teaching physics or teaching any discipline for that matter is incredibly complicated. There is no one size fits all pedagogy in those cases because every learning environment has its own unique challenges. And then on top of that, any particular pedagogical innovation is going to have different interactions with different kinds of students that have their own unique circumstances. So there's no one size fits all. But that being said, I do think that there is a fairly impressive corpus of literature that does have some suggestions for how we can think about the different ways in which we organize our learning environments might manifest in the different ways in which our students might cognitively engage with the material. And so I want to share some of those ideas with you today and in the context of the physics classroom, which, as I said, it's been wonderful to get back into the physics classroom over the last couple of summers and apply some of these ideas. And so before we get any further, I highly encourage you, if you have a mobile device, if you have a laptop or a tablet, quite simply anything that allows you to get onto the World Wide Web, I'd like you to go to braincandy.org, braincandy.org. You should see something that looks like this. Okay. So what I'd like you to do is click on the I am a student box. Click on I am a student. You can enter a code. And so when I teach the physics classes, I like to start Sesame Street style. And so today's colloquium is brought to you by the letter T, the letter V, the letter F, and the letter L. TVFL. And when you hit on that, you're going to now go to your student dashboard. And so just to reiterate, TVFL is the unique 4-character code for today. All right. And so I have a little homework assignment for you. So what I'm going to do is I'm going to pose a question. And so you should see that question now on your dashboard. And more specifically, you should see something that looks like this, okay? And so more specifically, I'm asking you the following question. I want you in just one sentence. I mean, if you want 2 sentences, that's fine. But I want you to somewhat succinctly, so think about it for a minute, somewhat succinctly summarize to me what active learning means to you. And again, active learning. I know you've heard that term. One of the things I'm going to talk about today is how that term kind of gets conflated with lots of other things. So what does active learning mean to you? Take a few minutes, enter it in that green text box, and then make sure you hit the send answer. And I promise you that your answers will come in completely anonymously. In fact, I've enabled things so that you can see what other people are sharing also anonymously. Take about another minute. So FYI, this brain candy technology you're using is something that I built when I was a graduate student, and I use it in every single class that I teach here at ASU. By the way, I'm an associate professor here. I'm in my 10th year now at ASU, and I use brain candy in every class I teach, in part because I do believe that providing students anonymous ways to share their thinking can sometimes ease the nerves and get more students to not only share, but maybe share in more candid ways. And I appreciate so many of you being willing to share your definitions of active learning. Now, the word cloud feature can kind of help me go through all of these responses and try to find trends. I know for sure, like I saw a lot of stuff about like working on problems. I saw a lot of stuff about collaboration. I also saw a lot of tautologies. I saw a lot of active learning involves learning that's active, right? You see the word active, right, is one of the most popular words. So that's a little bit tautological, but that's part of the point of this talk is to, okay, well, what does that mean exactly? What does it mean to say that learning is active? Does it mean you're doing jumping jacks while you're learning? I mean, or does it mean something different than that? But I really do appreciate you sharing these different definitions. And I think that the key here is that there's a lot of difference in these definitions, but there's definitely a form of learning that did not come up. And so that's this form of learning, okay? I didn't see a lot of stuff about listening to lecture, okay? Now the reality is that there is a time for telling, okay? You're going to be, I think, pretty disappointed if you just put kids around a table and tell them to come up with how to make sense of gravity, okay? There are certain foundational steps that are necessary from time to time, and sometimes, quite frankly, given the limitations of our education system, there is a time for telling. But I do think that having telling be the only modality is not really consistent with what the literature tells us. Now, that being said, I think that oftentimes that term active learning is given to reflect a variety of different things that are not that, okay? But the reality is that, I mean, we've even seen this in physics. I mean, we've got like the full studio models. We have the, the inquiry labs, the discovery labs. We've got the recitations, the tutorial approaches. Like we have a lot of different approaches that try to center the learning more on the student. They're all not that, okay? But they don't all necessarily promote the same level of cognitive engagement. And that's what I want to really dig into today, is I want to think about if we have a more precise definition for what active learning means, then that might allow us to better adjudicate different student-centered ways of promoting instruction, okay? Because again, there's lots of different ways that are not lecture, okay? But how can we adjudicate which ones might be more or less efficacious for our particular learning goals, okay? And so I believe that a framework I'm about to share with you gives active learning a more precise definition. And I think that we can really benefit from a more precise definition. And so again, we're talking about more precise terminology here. We're going to talk about how different forms of student-centered instruction might be consistent with different levels of cognitive engagement. And so what I'm going to share with you is a framework that's been developed by my colleague, Mickey Chi, in the Teachers College, and we call it ICAP. And so ICAP is an acronym for interactive, constructive, active, and passive. There's that active word, okay? Now active is going to get a more precise definition. Now, the idea is that Mickey and Mickey's colleagues went through decades of educational research literature, looked at all these different interventions, and looked at the outcomes of these interventions. And then what they did is they classified different flavors of interventions and looked how those different classifications of interventions associated with different levels of learning outcomes, okay? That's what this is based on. And so the idea is that as you move from passive to active to constructive to interactive, based upon, on average, the research literature over multiple decades, you tend to get, and again, on average, remember there's no silver bullets here, you tend to get on average deeper cognitive engagement as you move closer and closer to interactive, okay? Which is not the same thing as active, all right? And so let's get more specific here. And by the way, I also want to emphasize that what this is not telling you is that, you know what, you're not doing a good enough job until you always get here. That's not what I'm going to try to say. I'm going to make a case that this could be thought of more as a learning progression, okay? And that perhaps it's best to start here, but then to move to here, and then to here, and then to here. So what the heck would that mean? What would that look like? And that's what I want to try to unpack for you. So the idea is that understanding is not the same thing as learning per se. You can learn something, but not understand, okay? When we try to make sense of information, we have neurons that fire together and networks are formed. And it's possible that if you just, like, for instance, wanted to memorize pi out to 150 decimal points, right? By rote, you could do that, all right? You could learn those digits and recite them over and over again. But if you just did it by rote, if you just looked at the numbers and just tried to commit them to memory, you're not necessarily integrating them with other mental frameworks you have for making sense of information, okay? And so it's possible under the passive classification that a student could learn something, but not necessarily understand it. Sometimes this is called inert knowledge. This is knowledge that is in your long-term memory, but it's not really integrated with a lot of other stuff in the long-term memory. So it's possible that it can come online, but it's not as likely to come online because it's not connected to other things that could come online, okay? And now in contrast, active, okay? So now we're gonna give it a more precise definition. Active is when you actually have to activate some of your prior knowledge to try to make sense of that new information. So in other words, let's say that you have this new tidbit of information and you've got this prior mental framework to make sense of the world. And it's got, for simplicity, it's got category A and category B, okay? And then this new piece of information comes in and you want to classify it. Well, to do so, you first have to activate that prior mental framework, category A and category B. And then you might be like that goes in B, okay? All right, so that would be an example of how you would integrate this new piece of information into an existing mental model. First and foremost, that mental model needs to be activated. So this is a more precise definition of active. It's that your prior mental frameworks have now become active. That's not necessary with passive. You could just say out loud numbers and repeat them over and over and over and over and over again. In fact, there was a famous researcher called Ebbinghaus that literally just did these experiments on himself to just see how many things that he could memorize just by repeating them over and over again. That's not the same thing as understanding. Active is when you're at least going to activate prior knowledge to try to make sense of new information. But we can dig deeper. Constructive in the ICAP framework means that we're not just taking a piece of information and saying, okay, I have this mental framework of 2 categories, and I'm going to put this new piece of information here. Constructive means that you're making inferences now, okay? So in other words, I've got this existing framework that has category A and category B, and this piece of information comes along, and I'm like, that existing framework isn't quite suitable. I've got to make a new category C, okay? Now I'm making an inference, okay? I'm making a more elaborate neural network, all right? So, passive, inert knowledge, not really integrated with a lot of your other mental frameworks for making sense of things. Active, at least you're now getting some of those prior mental frameworks online. And constructive is now you're actually making new inferences. Okay, you've probably heard, many of you, the word constructivism. Okay, that's the idea behind this, is that old school views of knowledge are this more transmissionist view of knowledge where it's like, I have knowledge and now I'm just going to give it to you, right? And then you're just going to take it in and receive it. Okay, that's a really old school way of thinking about knowledge. Constructivism, which is much in line with this right here, is the idea that knowledge is not transferred, okay, from one party to the next, but rather knowledge is constructed. Knowledge is constructed by learners, okay? You could show the same piece of information to multiple people, and based upon different experiences that they've had in different mental frameworks, they might make sense of that information in very different ways, okay? So knowledge is constructed. And that means you're making inferences, you're making new mental frameworks. But it's one thing for an individual to make inferences and to construct their own meaning and understanding about something. And it's another thing to share your individual constructions with the individual constructions of someone else. When you're doing that, if you do it in a respectful way, in a considerate way, in a way in which you're really listening to each other, it's possible that you can have co-constructions that are greater than the sum of the individual constructions, okay? So that's the interactive aspect of ICAP. And so again, Mickey went through decades of research, classified different interventions, looked at the learning outcomes, and came up with this framework to think about different levels of cognitive engagement. But then how might we get them to one classification or another? So I'm going to walk you through some examples. So I think it's helpful to focus on note-taking here because you can see how what is ostensibly the same thing can actually be different levels of cognitive engagement. So for instance, if somebody was just writing down verbatim everything that I'm saying right now. I remember classes like this in physics where it was going so quickly that I had no choice but just to write down as fast as I could all the equations that were going up on the board. I was literally just a recorder. And then I'd go home and like 2 lines into it, I was like, oh no, right? So that kind of note-taking where I'm just recording something that's already given to me, okay? I'm not even activating my prior knowledge yet. I'm just trying to get this down on a piece of paper, okay? So verbatim note-taking would be classified as passive under the ICAP framework. Now, in contrast, let's say that you're taking notes and you're like, I'm gonna highlight this one because I'm gonna go back and look at that later. okay? Or, for instance, if you're in a class and the professor says something and you ask a clarifying question, so they repeat it again. Now, at least you're flagging certain bits of information that are given to you, and that flagging of that information is indicative that your prior knowledge is being activated so that you can eventually integrate the information you're flagging into your prior knowledge. So if you're going through and highlighting information that you wrote down verbatim, at least you're flagging certain places that you want to integrate with your prior mental frameworks, okay, which is different than just writing it down. So imagine there's a learning environment and there's the givens of the learning environment. If you just have a facsimile of the givens learning environment, that's passive. If at least you flag certain givens learning environment as something that might be of interest to you, that you want to study later, that would be what's classified as active, okay? But we can go deeper. Some of you might be familiar with Cornell notes, where there's a margin where the students write questions and have to put the notes in their own words. Now you're going beyond the givens of your learning environment. Now you're making inferences. Now you're putting things in your own words, okay? You're developing new mental frameworks for making sense of things. So like as a case in point, so since I started doing the lectures here in the summertime, I tell the students that I'm going to give them the lecture notes at the end of every week. But during the week, I want them to write the notes in their own words. And that's because I want to promote more constructive. Because if I just give them the lecture notes at the beginning of the week, it's possible they could just approach it in a passive way, or maybe they just highlight a few things in an active way, right? But it's not the same thing as putting the pen to paper and trying to summarize and put it in your own words, okay? I tell the students that the research suggests that they'll learn this more deeply. I'll tell them that I got their back. I'm still going to give them my notes. But when I do give them my notes, they need to realize that that's the way I see it. That's the way my brain has organized that information. And that might not be the same exact way that they see it, okay? And then what I do is during the lectures, I have what I call note breaks, where I encourage the students to take a break. So it doubles as a break, but it allows the students to talk to each other about the notes they took. Oh, I missed that. Thank you. Okay. So there's a difference between that and just giving them your slides. Okay. Then there's interactive. And this gets into what's really kind of my main area of research, which is argumentation. I believe really strongly that if we can support students in learning how to argue, that is learning how to adjudicate different standpoints by appealing to evidence and reasoning, I believe that if we learn how to argue, we can argue to learn, okay? And I'm going to get into this in more detail later, but this is in that spirit of co-construction. Now, you have multiple people making inferences and sharing those inferences with each other, co-inferences. So now that we have more precise definitions, I want to show you how this gives us greater clarity when trying to make sense of the welter of classroom practice. Okay, so this is a study where I use ICAP as my framework to make sense of high school physics classrooms. Okay, so this is based on a piece that I have in the Harvard Educational Review. And the basic idea is that I got the same high school physics teacher to teach 4 different periods of high school physics every day in 4 different ways. And we did that for 2 years. And we did that under the guidance of thinking about how teaching in different ways might promote different levels of cognitive engagement predicated on the ICAP framework. Okay, I'm guessing some of you are familiar with peer instruction. It's one of the things that really got me into physics education research. In fact, when I was in grad school, one of my nicknames was Clicker Guy, because I would carry around bags of clickers and go do studies with them. That's another reason why I developed Brain Candy, because it's a lot easier to carry around one laptop than a bunch of clickers. So peer instruction really started to gain steam in the late 90s, early 2000s. Eric Mazur, a physics professor at Harvard University, was one of the main advocates of it. And Dr. Mazur has been here several times. This is an incredibly influential technique in physics instruction, predominantly higher ed physics, but it's also found its way into K-12 as well. And the basic idea is that you get some physics lecture and then a question is posed to you, not unlike the active learning question I posed to you, right? Oftentimes, though, it's in the flavor of a multiple choice question. Is it going to go this way or is it going to go that way? So the student is asked to think by themselves, and then they would, back then, use the clicker, right? to vote A, B, C, or D. And so they would click on their vote, and then the professor would show the voting trends, right? Not unlike how I showed you the answers you were giving me to that active learning question. And so then the idea was that if you wrote a good question where you would get some variation in student responses, then instead of just saying, well, congratulations, everybody that got B, you win. Instead, you say, all right, we got work to do. We have yet to reach consensus, and our goal as a class is to reach consensus. And so turn to a neighbor and make a case for why you voted the way that you did, okay? And so that's where students would start talking to each other. They would get a chance for redemption by voting again. And what Eric Mazur and others found is that as we went through a couple of these peer instruction cycles of vote, discuss, vote, discuss, vote, discuss, oftentimes these physics students would begin to converge on the correct answer with very little additional work by the instructor other than encouraging them to talk to each other. And so that's encouraging, but just saying this works because it's active learning is kind of underselling it, because there's a lot of different flavors of talk that might take place, not to mention there's lots of other ways you could fill the time between clicker votes. So most of the peer instruction stuff that was coming out was essentially saying, here's a classroom with peer instruction and here's a classroom without peer instruction. And this one's better at teaching physics than this. And I wanted to dig deeper and say, okay, well, is there different ways of facilitating peer instruction that might even move the needle more, okay? And that's where having more precise definitions helps, right? Because it's not just whether or not you're having them actively engage in peer instruction, but different ways in which they can engage in peer instruction. And ICAP allows you to think about how those different ways might result in different cognitive engagement. So imagine this peer instruction cycle in a physics classroom. And so these are the high school classrooms that I went to. And so what we did is we had different classes spending their time between clicker votes in different ways, okay? And so we have our cycle. We've got variations in student academic performance and demographics that come into the classroom. And then based upon how they spend their time between the clicker votes, eventually the output, the dependent variable, if you will, would be to what degree they have conceptual learning gains. That's the basic framework here. But these different possible ways to spend your time between clicker votes, they are very much influenced by ICAP. So more specifically, same instructor. This instructor had 4 physics periods to teach. Again, this is high school. And so what they did was one period, and everything else, as you can imagine, is more or less the same, including the room, the clickers, the questions. But what was different was how they spent their time between the clicker votes. So you had the classic recipe, if you will, which is talk. So we had the students talk for 3 minutes and then they would vote again, okay? Now, talk would be more or less commensurate with ICAP interactive, okay? Now, in contrast, we had another condition where actually they would vote and then they would get 3 minutes of supplementary instruction, okay? Under ICAP, that would be more along the lines of passive, okay? And then there was a third period where they had a journal. And so they would click on their vote, but instead of talking, they would write in their journal the rationale behind their vote. So that's the right condition, okay? Our thinking was that's more along the lines of ICAP constructive, okay? And then we had a hybrid condition where we thought maybe the talk could be bolstered if they first had a minute and a half to think about their thinking on their own, and then they would share it with somebody else, okay? So that would be a combination of both constructive and interactive. Notice how the time on task is controlled here. It's 3 minutes between clicker votes, okay? We didn't want to do like 6 minutes here because we think that would be an unfair comparison with these other conditions. So we controlled for time on task, we controlled for the instructor, the classroom, the questions, everything. And to be even more careful, what we did was we repeated the study in the second year where we flipped the order of the conditions, because we find, especially with the younger kids, they get more restless as the day goes on, okay? So handing over the car keys in student-centered learning environments might be different in the afternoon versus the morning. So we also controlled for time on task and when that time was, okay? And so we flipped the conditions. So that also allowed us to control for the time of day. So in doing so, remember I said that the students come into the learning environment and they have all their unique demographic, right, and academic attributes. That's what this stuff is. So I'm building a model here where, and so some of you, because it was developed here at ASU, might be familiar with the force concept inventory. It's the most widely used conceptual physics inventory that's ever been administered for physics conceptual understanding. And so, and by the way, when I say normalized gain, so I gave the pre-test at the beginning, right, of the study, and then a post-test at the end. And so the FCI is out of 30 points. So if a student only gets 1 on pre-test, there's a lot of gain they can possibly get, right? So you can normalize for the gain by simply saying, okay, well, if a student got 28 at pre-test, they can only possibly gain 2 more. So if they got 29 at post-test, the raw gain's only 1, but the normalized gain's 50, right? Because they got 50% of what they possibly could have got. So normalized gain is a dependent variable. That's the output. And I can build the statistical model to explain the variability I see in different normalized gains for different students. And so I can think about the demographic information, but then I can also think about the different conditions that they were in. Remember, write, talk, write plus talk, okay? And then finally, I can also add in time of day, all right? So I have this 3-pronged model, if you will, demographic information, experimental treatment condition information, and time of day. And I can use that to explain more and more of the variability in my output variable, which is the normalized FCI gains that are demonstrated by the students. And so what was pretty cool is that this is a school that was almost 60% Title I. These kids that did peer instruction, on average, regardless of condition, had FCI gains of 33.7%. For the Harvard students, the original peer instruction studies that were not using peer instruction, so they were just taking regular calculus-based physics at Harvard, their gains were only 23%. These are college students at Harvard versus high school students at a school that's almost 60% Title I. That's encouraging. Now, here's the thing with ICAP. Remember how those different conditions, right, could be thought of as constructive or interactive and so forth? It was the talk condition that reigned supreme, okay? The talk condition showed a statistically significant improvement over any of the other conditions, and it raised their normalized gains by 7%, okay? And so that makes you think, okay, well, you can say, well, it's just a clicker classroom or not, or you can go deeper and be like, okay, what's a clicker classroom, but then we're gonna spend our time in these specific ways. And so by having the students engage in more ICAP interactive activity, it does potentially promote deeper understanding. And so then how the heck do we actually promote more interactive engagements? Because it's a lot more complicated than just saying, hey, talk kids, right? Because in many cases, like if you just tell the kids to talk and you walk around the room and try to listen to what they're saying, like the student's like, what'd you get? And it's like A, and the other student's like, I got B, okay. And that's the end of the conversation, right? So, you know, right? So how can we promote more interactive engagement? Well, I'm gonna make a case for 2 big reasons why I really think that confusion and uncertainty can be a really good thing. And so the first case I'm going to make about confusion is that I think when science classrooms say, okay, today we're going to talk about such and such. First of all, you're telling kids you're about to give them answers to questions they didn't ask themselves. So that might compromise motivation. But then if you really look at how most science classrooms take place, certainly at K-12, it's usually, we're going to talk about such and such today, and we're going to talk about it in this nice, one-sided, logical, coherent explanation of how scientists today think you should think about this phenomenon, okay? It's not very messy. It's like, if you want to understand photosynthesis, here you go. Here's what you should think. And so I think that that's a little bit problematic because it inculcates a mindset that science is clean, neat, orderly. There's not a lot of controversy. It's right or wrong, right? When in reality, there's many shades of gray and it's incredibly messy, right? And I think that promoting confusion in classrooms where students are not just given one way of thinking about things, but are given alternative ways of thinking about things, that confusion can actually be really healthy. And one of the ways in which I think it's really healthy is that it causes you to pay more attention than you might normally do. So I think a study that beautifully illustrates, so Derek Muller was looking at how you could use multimedia to improve physics instruction. And so if you can imagine, the students were given these videos and like, here's a person shooting a basketball. And so they freeze it and they give you these multiple choice questions where, you know, what's the direction of the gravitational acceleration, right? And so the students need to answer this, but here's the thing. Before they answer it, they get treated to some explanations of how to think about this problem, okay? So there's one condition where, if you can imagine, somebody comes on the screen and they tell you how you should think about gravity and how it affects the basketball, right? And so they'll give like an explanation. Well, okay, so there's a ball and gravity at all times, right, is pointing down, okay? And near the surface of the earth, we can treat that acceleration as roughly constant, right? And so they get this explanation of how to think about the gravitational acceleration near the surface of the earth. Okay, so imagine one condition where that's the only explanation they get. Okay, they just get the nice single one-sided coherent explanation. Okay, now imagine condition number 2 in Derek Muller's study, where they get this explanation, but then this other person comes on the screen and they say that, no, this is how you should think about it, right? The ball's going up, so there must be some upward force that's winning. And then it looks like gravity catches up, and oh, they're equal, right, when it comes to a stop. And then now gravity starts to win, right? It's a very common preconception that students have in describing throwing a ball into the air. So in condition number 2, the students got both explanations, not just the one that was coherent, okay? Okay, so get this. The students did pre-test, post-test. The students that were given the single one-sided explanation showed no statistically significant difference from pre-test to post-test. They didn't learn anything, okay? Meanwhile, the students that were given these 2 different ways of thinking about things showed statistically significant improvement from pre-test to post-test, okay? Here's where it gets really interesting. The students were asked to rate their confidence, okay? The students in the condition where they just get this nice, crisp, one-sided explanation, they were confident. They felt good. The students in the condition where they got 2 different explanations, they're like, what's going on? Why are, what, right? They were not confident. So the students that were not confident did better. And what's even more interesting is they also asked the students to remember what was it that was in the video to begin with? Students over here that were given the one-sided explanation would say that there were things in the video that weren't in the video. And the reason being is that when somebody just gives you this nice, logical, coherent, one-sided explanation of things, you're kind of like lured into this false sense of security where you're like, yeah, that makes sense. Yeah, I got that, right? We've all been there. And when you are lured in that false sense of security, you're not paying your utmost attention. And that's when you project some of your prior thinking onto the information that's being presented. Meanwhile, if you, instead of just laying back and just letting the professor do all the explaining, if you're like, okay, well, it could be this or it could be that, it's on you to figure it out. Now you're paying more attention to, okay, what do I do here? Okay, you might be more confused, but you're paying deeper attention. I'm also going to make a case that confusion is good because it's an essential ingredient in feedback loops. So why the heck would I care about feedback loops? Because feedback loops are another way of talking about what we call cognitive articulation cycles, where the literature does very much suggest that the more and more and more articulation cycles you have when you're thinking about something, the deeper your learning and understanding of it can be. This was from an article in Wired magazine, where there was a school where people kept speeding through the school's speed zone, and they couldn't get people to stop, and they were giving tickets out, and people just kept speeding by. But then what they did is they installed these dynamic speed display signs, and you've probably seen these, right? And here's the thing, like, the speed display sign just tells you how fast you're going. That's not really unique information. You can look at your dashboard on your car and see how fast you're going. But here's the key. It gives you a readout that lets you monitor what your performance is, but then it posts it next to the speed limit right? That is the law, okay? This is the normative, what you ought to be doing, and this is what you are doing. And so this actually gets into, if any of you are familiar with Albert Bandura, an incredibly famous psychologist, he was a pioneer of what's called social cognitive theory. And this really gets at the heart of social cognitive theory, because the idea is that if we can monitor our performance, and then we can get a measure of how our performance stacks up against the performance of others, if there's a discrepancy between our performance and the performance of others, so there's a discrepancy here, right? 29 versus 25. A discrepancy between the monitoring of our own behavior and the behavior of others can motivate us to try to reduce that discrepancy. It can try to motivate us to change our behavior so that our own behavior is more similar to the behavior of others. So in other words, I'm going to let my foot off the gas a little bit to get closer to 25. And I actually find the opposite too. If I'm driving by one of these things and I'm below it, I'll speed up a little bit. Okay. Another great example of this is like, like fitness trackers with your watch, right? It'll tell you like, how fast your run was. But what's really helpful is that you can also see what other people did, right? And that can be motivating, right? In your training. So essentially, peer instruction is a series of these feedback loops where you're monitoring what your own thinking is, and then you're seeing how it compares to other people, and that can motivate you to react. And that includes motivating you to talk to other people to try to figure out how you can reduce that discrepancy. But the issue here is that as you're motivated to talk to other people to try to reduce that discrepancy, not all talk can be created equal, okay? And so I believe that technology like the Brain Candy platform that I've built can provide ways in which we can kind of nudge students and support them to talk to each other in increasingly interactive ways, okay? Which is not the same thing as what'd you get? Okay, right? Where students get practice at listening to each other, okay? And trying to figure out where they agree and disagree and how they can build off of each other's ideas, okay? And so we have about 5 more minutes before Q&A. And so I am going to ask you to return to your Brain Candy screen, because what I'm going to do is I'm going to turn on a thing that I call PAL mode. And so this is based upon literature about listening, about affirmation, and about co-construction. So for instance, if you can imagine posing a question to kids where they have to actually argue their case, all right? I believe that especially when they're first getting started with this, they need a scaffold, they need supports. And so now, instead of just filling in your answer in the green box, you get this step-by-step guidance as to how you can adjudicate your position with the position of someone else. So PAL is an acronym where P is paraphrase. So this encourages listening. Okay, so before you write your answer down, you first have to paraphrase what the other person thinks. Okay, then align is an approach to argumentation where instead of just saying, oh, you're stupid, no, you're stupid. Instead, you start with where might the common ground be, right? I would argue that it's probably better, like if there's a debate about, say, vaccines for children, right? It's probably better to start with, hey, let's all agree that we all love our children, okay, and we want the best for them. Start with what you got in common before you get into the stuff that you don't. And then once you enter that, this third box pops up where you have to, if possible, acknowledge something that you might have learned from the other person, right? By them sharing their perspective with you, okay? And then finally, after you go through those steps, you fill in the green box, okay? And so we have a couple of minutes. Let's try that. Turn to a partner and again, approach this active learning question, but now share your perspective on active learning with somebody else. And if you have time, try filling out these boxes. Oh, one more minute. Hey, everybody. I think like, especially compared to like my experience with the I mean, I've never been in this classroom. And so I mean, when I first started experimenting with ways to shift the learning environment that I learned with students and having that volume, I would just love it. And have this good feeling like not see something going on. But I hope that maybe through a framework like ICAP, it might give you now like a little bit more refined sense of like how you can get into that volume, right? And think about how it's not enough just to say that they're going to shift the dynamic from the instructor to the student. There's different ways in which student-centered activities can transpire, and that might mean that's a different cognitive. And so I very much hope that the framework I shared might at least give you like some, general rules of thumb about how you're structuring your I can't thank you enough for your time and your attention. Really quickly, I've got 2 confused participants. So in the Brain Candy platform, I have a thing called confusion checkbox, which has been enabled. Confusion checkbox is a way of raising your hand without raising your hand. And this gets back into, I remember being in a lot of classrooms where, quite frankly, I think a lot of students were scared, particularly if they were underrepresented students. They didn't want to be conflated into stereotypes. They shouldn't be there. And so if they raised their hand, there was extra pressure on them. And so confusion checkbox is a way of raising your hand completely anonymously. And so it tells the instructor how many people are confused. You can even have it play a sound if you're not at your computer. But how do you actually address the confusion? Well, I have a thing I've built in called Scribble Pad. And so you'll probably be able to see on your screen now that it's this Scribble Pad, send a scribble. So if anyone that is confused wants to send me a scribble, I can actually write directly back to your screen, but it preserves your anonymity. Okay, so you can have a back and forth with the instructor and all the time still be anonymous. Because I really do think that anonymity can sometimes be beneficial in allowing people to say, I'm confused. Can you please stop? Can you please slow down? Oftentimes we psych ourselves out and think, oh, I must be the only one that's confused. When in reality, if you're confused, probably other people are confused too. So this is a really good formative assessment tool for teachers to know when to pump the brakes. Also, I encourage you to use ScribblePad to send me your email if you're interested in a Brain Candy account, because I've made this a nonprofit where it stays completely free in perpetuity. And so if you want access to this in your own practice, you can totally have it. Just send me your email and I'll sign you up. So in terms of the studies that I chose to highlight today, I'm guessing we'll probably share these lecture notes. And so I provide the full references for the ICAP framework, for the peer instruction study that I used ICAP to try to make sense of the physics classrooms, and then the video explanations of the one explanation versus having to adjudicate 2, Derek Mulder's study. There's the full citations there for all of you. And so truly, thank you for your time. And I guess we'll do questions now.
Okay, thank you.